Hello and welcome to the KCSE Physics Paper 1 of the year 2022, the complete marking scheme. And I want to go straight to the first question. Of course, this is the first page where instructions are given. I would recommend that you always read these instructions carefully. Although these instructions have not changed for a number of years, so get the habit. When you're revising, read through these instructions so that you can quickly identify if there are any changes. Let's go to the first question. This first page, especially this table here, is meant for the examiner's use, and we actually don't need to do anything to that particular page. Let's go to the second page where we are at the first question here. Question number 1, state what is meant by area. This is a very simple and direct question. And I'd like you to be aware that simple questions are also set at this level. So don't always be concentrating on difficult questions and you avoid the simple concepts. For example, area. What is area? Area is a measure of surface. Of course, area is the first derived physical quantity that we study in physics, because the first section deals with the 7 basic physical quantities, which include length, mass, time, and so forth. And then the other physical quantities, which are not basic, they are derived. And area is the first one. So it is a derived physical quantity, and it is defined as a measure of surface, or you can say it is defined as a product of two lengths, because the way we define a physical quantity is by indicating how it is obtained. So the SI unit obviously is square meters. This is the unit written as a complete word, and this is the short form of the unit. So it can be written like this or like this. You'll get all the marks. Then the next question is about forces. Explain why water in a glass tube forms a concave meniscus. Now, what are we talking about here? This is what we are talking about. If this is the glass tubing, like that, and you put water in that glass tubing, find that it forms that kind of curvature. This is what we call concave meniscus. If it was mercury, it will form convex meniscus, but this time it is water. So what do we expect here? There are two types of forces which you must mention. You must mention cohesive forces between water molecules and adhesive forces between water molecules and glass particles or glass molecules. So it's about which one of these two forces is larger than the other. So you're going to say that. So that is how you answer that question. So let me emphasize adhesive forces, because some students are in the habit of just saying adhesive forces is greater than cohesive forces. You must mention adhesive forces between which molecules. Okay, so adhesive forces between water molecules and glass molecules is greater than cohesive forces between water molecules themselves. Let's look at question 3. And here we are at question 3. What are we asked? We are told that figure 1 shows how water is drawn from a large tank into a low-lying container using a rubber tube. And we know that this is how actually the siphon works. Explain how the process takes place. So first of all, we must fill up this tube with water, that liquid which we want to transfer from the container. So fill up the tube with that liquid. We can do that by reducing the pressure in this tube so that it is lower than atmospheric pressure by sucking or at this end. So when we suck at this end, the pressure inside the tube is going to be lower than atmospheric pressure, and the atmospheric pressure is going to push that liquid into that piping. Now the open end, this other end here, must be lower than this surface of the water. Must be lower, at least that one has to be mentioned. There has to be this height here in such a way that the open end is lower than the surface of the liquid in the larger container. The open end of the tube must be lower than the surface of water in the larger container, or in the container from which we are transferring water. Now, why is that important? We need to consider this point, the pressure which is acting on the water at this particular point. That pressure must be atmospheric pressure plus this depth of the water column, which you're going to call X. So the pressure at this point must be atmospheric pressure, which we can give capital H, plus the height due to the water column. When you come to this other end here, you find that the pressure at this point is much higher than the pressure at this point, because it will be atmospheric pressure plus pressure due to this liquid column. So at this other end, we're going to have H plus rho Hg. At this end here, we have atmospheric pressure plus rho Xg. So which one of these pressure is high? Of course, it is this pressure here, because you can see the only difference between this equation and this equation is the value of H. Because you can see the difference between this equation and this equation is just the value of H being greater than X. So pressure at this point is higher than pressure at this point. So it is higher than atmospheric pressure. When we look at the fluid which is on the outside, it is air, it is atmospheric pressure. So at this point, the pressure is higher than atmospheric pressure. So when you compare the two, we find that excess pressure will make the liquid to come out. So you can see at this point, the pressure of the liquid is higher than atmospheric pressure. So you can write all that literature in this particular space. Let's go to question 4. Suggest how a piece of paper can be used to demonstrate that matter is made up of tiny particles. Of course, this is one of the experiments. This is the first experiment which we do when we want to show that matter is made up of tiny particles. You get that piece of paper. We subdivide it into smaller parts. We cut it like that. Then we take the other one, we cut it into 2. We take the resulting, we cut it into 2. We continue like that, cutting the piece of paper into smaller and smaller particles. So we start with a big paper, we cut it into 2. We take 1/2 of that, we cut it into 2. Then we take that half again, divide it into 2. We continue like that until at the end it will not be able to use that pair of scissors to cut that final particle. If you are to imagine that you're going to put together those other particles in order to form the original particle, you will find that the original paper can be formed by putting those other very small particles together until you get the original paper. And that is proof that when you see this original paper, it is made up of other tiny pieces of paper. And so is every form of matter. If you take a piece of chalk, for example, you're able to repeat this process like this until you come to a very tiny particle which cannot be split any further. So the idea of taking a pair of scissors here, because we are dealing with a piece of paper, you'll have to talk about using a pair of scissors or using a scalpel. Cut the paper into two, then continue the process of cutting the resulting papers into two. A time will come when you have a very small piece which is not possible to cut any further. That is proof that the original paper is made up of tiny pieces of paper, and that applies to all forms of matter, whether it is a solid, a liquid, or a gas. And that is how you would answer question 4. Again, I've noticed that if I start inking these spaces, it's going to take, the video will be very long, and I don't want that one to happen. So I'm just going to explain, and then you can write down the points as I explain. Now, question number 5, we are told that figure 2 shows 6's maximum and minimum thermometer. Explain how increase in temperature causes index A to move upwards. Now, this is basically what happens. A maximum and minimum thermometer is a temperature. A maximum and minimum thermometer is a thermometer which measures the minimum temperature of a given duration of time, as well as the maximum temperature in the same duration of time. Say, for example, in a week, we want to know what was the maximum temperature ever reached and what was the minimum temperature ever reached. In this question, we just want to show how the maximum thermometer works, because we have been asked to explain how an increase in temperature causes index A to move upwards. So this is what happens. This thermometer has got one bulb which is full of mercury, and it is a section which is used to measure minimum temperature, while the other section has a space above the alcohol. So this space is filled with alcohol and alcohol. At the very bottom, we've got mercury. Now, when temperature rises, the alcohol in P is going to expand and push down this level of mercury. Consequently, because liquids are incompressible, this other level of mercury is going to push this index A upwards, like that. So when that index A upward rises, it also pushes this alcohol upwards, because there is a space into which alcohol can move. Now, when this level moves down, this index B is not affected. It remains in that position. But because the alcohol just passes just through it, like that. These indices, they've got springs which hold on to the sides of this glass. Now let's see what happens when temperature falls. When temperature falls, this alcohol is going to contract, and this level of mercury is going to move down. When it moves down, again, this index is not affected, so it remains in the position where it was. But this other level, this other index B, is pushed up. So you can see that these two indices only move when the mercury is moving upwards. So when there is an increase in temperature, this level moves down, so this index does not move, but the index on the right, or the index A, moves up because this mercury level is moving up. It pushes it up like that. Now what happens after that duration, and we need to reset this thermometer? We just use magnets in order to, because these are steel indices, so we just use a magnet to pull it down, and this magnet again to pull it to the set position. And that is how an increase in temperature causes index A to move upward. So in order to explain this part for 2 marks, you need to mention a rise in temperature causes the alcohol in bulb P to expand, pushing this level of mercury down. The mercury just below index A pushes index A upwards as alcohol in Q is moved into this space here. Okay, when temperature falls, of course now you don't need to go into that, but I'm explaining exactly but I'm giving the complete explanation of what happens with this thermometer. When temperature falls, this alcohol is going to contract, so this means that this level of mercury is going to move up, pushing index B upwards, while the alcohol just passes through index A as this level of mercury falls. And that is the explanation you would give in order to earn these 2 marks. Let's go to question 6. In question 6, I've already written down the answer. The difference between heat and temperature. You're supposed to say that temperature is the degree of hotness or coldness of an object, while heat is a form of energy which is in the process of transfer from a body at a higher temperature to one at a lower temperature. So it's just as simple as that. Again, it's a very simple question. When we do thermal expansion or heat transfer, this is where your teachers start from. They start by distinguishing between heat and temperature, so that we don't want you to confuse between these 2 physical quantities, temperature and heat. And remember, it's only referred to as heat when it is in motion, due to temperature difference when it is in motion. Once it is in a body and that heat is no longer being transferred, it's no longer referred to as heat. It's given another term which we don't study here. It is given the term internal energy of the substance. So that is how that question is tackled. Let's go to question number 6. State 2 factors that affect the stability of a cylindrical container. Now here we have just been asked to state, not to explain. So one of the factors which affects the stability of solids is the area of the base support, the area of contact between that solid and the support is what determines its stability. Of course, the larger the area, the more stable the object will be, because it can be tilted through a large angle before it tilts. But that explanation is not required, because you are just required to state. So it is the area. The other one is the position of the center of gravity. Is it high? Is it low? Again, we just need to state the factor, position of the center of gravity. If you're required to explain, then that one is totally a different question altogether, because you will say, if the question was state and explain, you will say position of the center of gravity. By doing that, you have stated. Then the explanation will be the lower the center of gravity, the higher the stability, because again, you can be able to tilt it through a large angle before it topples over. Let's look at question number 8, which is about calibration of a spring in order to use it as an instrument to measure force, as a force meter. We're told that figure 3 shows a setup in which a spring with a pointer is attached to a wooden strip that has a hanging hook. A graph paper is fixed along the strip to be used to calibrate the spring. So we've got this wooden strip here. This wooden strip is just to remove kinks in the spring, yeah, and in order to keep it straight. So what we are going to do is this: we are going to identify the position of the pointer on this scale and maybe call that position 0. Then we suspend the 100-gram mass 100 gram mass, which is 1 Newton. 100 grams is 1 Newton. Then this is our argument. Of course, when we suspend that 100 gram mass here, this spring is going to stretch and the pointer will come maybe to some point here. Then we are going to identify that position as 1 Newton. So on our scale, we are going to write 1 Newton. Then that is all we need to do, because the rest of the working is like this. We are going to identify the length of this extension, because this is the size of the extension, and then we repeat that extension here. We put a mark here and call that mark 2. Then we use the same extension, put another mark here, we call it 3. Another mark here, we can call it 4. What we are doing is that we are putting markings on the instrument in order to use it to measure force. Now we are going to take the space between 0, the 0 mark, and the 1 mark, and see whether it is possible to subdivide that space into other smaller distances. For example, we can see that here it's possible to put a mark here. It's possible to put a mark here, so that now we can call this one 0.5. Although we won't write 0.5, but at least we can say it can be able to measure in steps of 0.5. Then we put another mark there, and again another mark here. If it is possible to divide that 0.5 into 5 divisions, so that each and every division now will be 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, then we can further subdivide that space into 5 more divisions. So the numbers we use are 5, 10, 20, and so forth. And once we have those numbers clearly marked on this space here, then we have calibrated the spring to be a spring balance, or we have calibrated this spring balance. So point number 1, note the position of the pointer on the scale when there is no mass on it. Suspend the 100 gram mass. Note the new position of the pointer. Because 100 gram mass is the same as 1 Newton, indicate 1 Newton against that mark. Then repeat equal amounts of extension moving in steps of 1 Newton. Mark these extensions or these distances on the instrument. If it's possible to subdivide the spaces between 0 and 1 Newton, I'm talking about this because maybe this spring may be too stiff and you find that it may not be possible to subdivide this particular space here. Once the markings have been put on the instrument, then it has been calibrated. So again, you can try to summarize that in this particular space here. What is important is about putting a mark when it is carrying no weight, and putting a mark when it is carrying a weight of 1 Newton, and then repeating that extension on the instrument, or marking that extension on the instrument. Let us look at question number 9, where we are told water enters a pipe at a velocity v1 at a point where the cross-section area is A1. So this is the situation. There is this point here. This particular space here, or this particular cross-section of this pipe, is A1. And then it enters another region where the area, I'm going to say that is a little bit wider, It can start from a narrow pipe into a wider pipe, or from a wider pipe into a narrow pipe. It really does not matter. Then after that, we also identify this area and call it area 2, like that. So the speed of this water here is V1, and the speed of this water is V2. So water enters a pipe at a velocity V1 at a point where the cross-section area is A1. It leaves the pipe at a velocity V2 at a point where the cross-section area is A2. Show that this is the case, that A1 V1 is equals to A2 V2. Here we are going to use the fact that because the water is incompressible, then the volume of the water which flows through a given cross-section area per unit time in the narrow section is equal to the volume of the water which flows through the wider cross-section, again per unit time. Let me say per unit time, maybe it flows, the volume of the water which flows through that pipe is this much. And then when it comes to the wider pipe, you'll find that this volume will be here per unit time. So this volume of the water and this volume of the water is the same because this liquid is incompressible. So we are going to say that that volume can be given by the cross-sectional area A1 times this length which it covers per unit time, D1 times D1 is equal to the distance this one moves like this is D2. So it's equal to this volume, which is the cross-section area, times D2, like that. But D1, but D is equals to speed times time. So here we've got A1, D1 will be equal to V1 times time. This is A2. A2 D2 is going to be equal to A2 times D2 will be V2 times time. And you can see the times, they are the same. Since the times are the same, then we end up with A1 V1 is equals to A2 V2. So we can use the idea of volume. We can also use the idea of mass, in which case now we'll be talking about something called the mass flux. Here we are talking about volume flux, the volume of the water which passes this cross-section area per unit time. If we use mass flux, then it will be the mass of the water which passes this cross-section area per unit time. And that is how you can prove that equation. Let's go to question 10. We are at question 10 here, where we are told, sketch the displacement time graph for a body moving with decreasing velocity. Displacement over here. So this one will be displacement S, and this one is time. So we have to remember that the gradient of a displacement time graph represents velocity. Gradient of a displacement time graph represents velocity, and velocity is decreasing, so the gradient must be decreasing. So we start with a high gradient at this point and you show decreasing gradient. Yeah, you start with high gradient here, and the gradient is going to decrease as time increases, and that is how you answer that part. So let's look at this question. We are told that figure 4 shows a graph of force against time when a tennis ball is hit. This one here. Determine the mass of the tennis ball whose velocity is 60 meters per second, assuming the ball is stationary before it is hit. So let's see. Over here I have the racket. The racket is here. There's the racket. And here we've got the tennis ball. So it is the racket which is moving towards the tennis ball. So there is going to be a point that the racket which is moving very fast just makes contact with the tennis ball here. It just makes contact with it. That is this point that we have here. Just makes contact. Then as time goes by, and these time intervals are very, very short, the tennis ball is hit and starts to lose shape. So here the speed of the tennis ball, because it was stationary, is 0. Here it starts to gain some speed in that direction as it loses shape. So time comes when it loses its shape completely. And this is where there is a maximum force exerted on it. And that one happens at this point. Yeah. So it's at this point that now the tennis ball starts to gain velocity. So a time comes when the racket is just the ball now has regained its shape completely. Remember this point where there is maximum force acting on the tennis ball is this point here. Then a time comes when now the ball starts to regain its velocity, in this direction, and this velocity, we are told, is the one which is 60 meters per second as it moves in that direction. That is the final velocity that the ball leaves the racket with, like that. So I think at this point the force acting on it is now 0. So this other point here is this one. So let's look at the ball. The ball starts to gain momentum from this point, because that is when its velocity starts to build up until the point where the ball just leaves the racket. At this point there is maximum force on it, but it hasn't yet gained maximum velocity because the tennis ball still has got to regain its shape with maximum velocity. So one of the reasons why it gains this speed is because of the way it regains its shape and the fact that the racket has pushed it to the right. That is where it gains that velocity. So we can say there is change in momentum of the racket. There is change in momentum, and this change in momentum is mass times change in velocity, which is v minus u, which is equals to m times the final velocity of the racket is of the ball is 60, the initial velocity is 0, and this will become equal to 60m. That is a change in momentum. Change in momentum, yes. But then we remember something, because this one is a force time graph. Change in momentum is actually equal to impulse, and impulse is force times time. And when you multiply force times time, when you multiply this length by this length, you're actually getting area. So, and this area is actually the area of a triangle, a half base times height. So we're going to say this change in momentum, which is 60 m, is going to be equal to a half times the base, which is 50 by 10 raised to minus 2. That is like 50 divided by 100. That is the base. And then the height is 500. So let's see what happens here. So this is going to be equal to 60 m. It's going to be equal to 25 divided by 2. This like m is equals to 25 divided by 2 divided by 60. We divide both sides by 60. So that is 25 divided by 120 kilograms. And this, of course, it gives us, let me just work out, 25 divided by 120, 0.21, 0.21 kilograms. That's like 210 grams. That is my view, is the way we were supposed to work out that question. Let's look at question 12. Question 12 is about energy transformation that takes place as a pendulum swings. What is the situation here? This may be the support for the pendulum. It is displaced through a certain small angle there, and it starts to swing. This is its equilibrium position. So let's look at the energies that it has in these different positions. When it is raised to some height like that, what it has is gravitational potential energy. And remember to mention the word gravitational potential energy, because there are two types of potential energies. There is gravitational potential energy and there is elastic potential energy. So gravitational potential energy is due to position, while elastic potential energy is due to the state of the body. So this one is mgh. As it swings like this, it loses height, and therefore the gravitational potential energy is decreasing until at some point here it's got maximum velocity, and it's sort of, at that instant, it is sort of moving horizontally. So it's got kinetic energy, maximum kinetic energy. So the interchanges of energy will be from potential energy, depending on where the ball starts from. If it starts from here, it's gravitational potential energy to kinetic energy. And because it doesn't stop here, it swings to the other side here. If there is no air resistance, then it rises to the same height, in which case now the kinetic energy it has here is converted back to potential energy. So those are the interchanges of energy from gravitational potential energy to kinetic energy, back to gravitational, back to kinetic energy, and so forth. Question number 13. When determining the specific latent heat of fusion of ice by electrical method other than mass, which is m, voltage, which is V, current I, and state one other measurement that should be taken. Of course, we know that the heat energy is going to be equal to power of the heater times time, which is going to make a certain mass of ice to melt multiplied by the specific latent heat of fusion. So this power is current times voltage, which has been measured, times time is equals to m LF. So what is remaining, or what must be measured, is the time for the mass m of ice to melt. That is what is missing out. And that is how section A is worked out. Let's take a short break And when we come back, we'll move over to section B.